Happy Tuesday. My hair's all crazy. Hope you guys are doing well. This is our last video for the year. That's crazy. We made it through what, like 7 weeks or something like that? Oh, it's a long time. But anyway, this is our last video. So this is our last week of new stuff. I will definitely for sure be around though if you guys have questions about stuff moving forward. It was announced this morning. I don't know if you heard the phone call this morning. There's no final exams. Yay! I think we're all pretty happy about that. I lost my train of thought. I looked over at my phone and I lost my train of thought. See, that's why you shouldn't have your phones in class, because you can't pay attention. Have your phones in class. But I will still be around. Next week will be a good time for you guys. If you have anything that's incomplete, most of you are fine, but there's a handful of people that have some incompletes out there. All the assignments are still open. Quizzes, homeworks, everything are still open until I think I put the 19th. So if you are missing anything, please go in and do it. And if you do, please let me know that you have done it, because I don't get alerts or anything from Alex or Teams or anything that says, hey, this person finished this assignment. So if you do go back and do any makeup work, please, please, please send me an email, let me know you did it, or send me a remind text or something. And then I can go in and I can update stuff in the gradebook. Okay, our last video. So this is gonna be a fun one, because this is like sort of some intro calculus stuff. And this is not something that we typically go over in pre-calc, although we probably should. Sometimes we just run out of time. But it would be a great service to the calculus teachers for us to save a little bit of time and go over some stuff. There actually was one other topic that those of you that are going to go into BC would have been great if we'd had like one more week to present some new material, because there's another topic that we actually were going to do. We had these two. We had partial fractions, which again only really applies to the BC class. And we had this thing that I'm about to talk about called the difference quotient, which applies to everybody taking calc. So we decided that partial fractions would have been a little bit hard to do in just one video. It's a lot of stuff. So if we had done it in class, it would have taken us a couple of weeks. So it was way too much stuff to just try to cram into one video. But difference quotient is a little bit easier. So we decided to try to, excuse me, do that as our last thing. Having some issues today. I don't know if it's allergies or what, but it's very dry, so bear with me. If you hear me stop while I'm teaching, I'm trying to probably drink something and not die from coughing. So that's what I'm going to do and talk about difference quotient today. Like I said, this is not something that we typically go over. So, and it's definitely not something that I would purposely choose to teach through a video. Not that it's hard, but I would much rather be with you so that you can ask me questions. Because I feel like there's probably going to be some questions, but I don't think it's that difficult. Hopefully I'll do a good job explaining it. And there's going to be some visual aids and it'll be fun. Okay, but before we actually get into the difference quotient stuff, have to go backwards a little bit and just kind of go over some more algebra-ish stuff, specifically some stuff related to function notation, which I know seems pretty basic, but I just want to make sure that we're all on the same page going into this, and that you guys get a little refresher, because there's part of this that is a little bit tricky. And I think that that is the part where if I'm going to lose people, that is going to be where it happens. So I just want to do a little refresher really quick, spend a few minutes, and then we'll get into the actual difference quotient stuff. Okay, so let me switch over here. Oh, I've got too many things going on down here. No, that's not what I need to do. I'm sorry, I'm all over the place today. Okay, here we go. So I gotta share first, and then, all right, let me make sure I'm all in focus. Okay, so the first thing that we're gonna do is we're gonna, like I said, talk about function notation. And this is not something new to you guys. So just so you know, and I'll talk about this again later, but you guys will have just a few practice problems to do for homework this week, and they're going to be in teams. This is not an Alex thing. This actually is not part. Alex draws from our pre-calculus textbook, and this is not really a pre-calculus. Well, sometimes it's in pre-calculus textbooks. It's not in ours. I wish it was, but it's not. So I have just like a CUDA worksheet that I'm going to post in Teams under the assignments tab. So that's where you're going to go look for your homework this week. I kind of lost my train of thought again. I don't know where I was going with that. All right, but anyway, function notation. So again, this is not something that is completely new to you guys. So let's say that we have a function. We're going to do just a quadratic function. I've got 3x squared minus 4x minus 5. So when you guys, way back whenever you started to talk about functions and algebra and stuff, and you kind of started to talk about function notation, one of the first things that you did was learn how to evaluate functions, right? And so probably like super early on, this didn't even say f of x. It would have said like y equals blah, 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 blah. And then you got a little fancier and you started to use f of x. And so some of you may have forgotten what this means, but we use f because it's a function. So we're saying this is a function of x. X is the variable in this function. This is a function of x. That's what this notation means. Some of you right now are probably going, oh yeah, okay. So that's what that means. F of x, a function of x. But if I wanted to evaluate that function, let's say we wanted to do f of 4, right? We want to know what is the value of the function when x is 4. That's what this is sort of saying. This is a mathy way of saying this is the value of the function when x equals 4. So hopefully we all know that we would just plug in 4 and we would work this out. And I believe if I did all my math right, this turns out to be 27. So the value of this function, this quadratic function, the value of this function when x is 4, the value of this function is 27. So you can think about this a few different ways. That means that we have the point 4, 27, right? That would be a point on our graph. I could also write, I could say, let me think about how to write this. So we could say like x equals 4, y equals 27, that kind of thing, right? So we're just evaluating the function, but we don't even have to evaluate it at a particular number, right? That's typically what we do. But you could also have like, what if I wanted to find f of a? Well, okay, that just means instead of plugging a 4 in to the variable, we're just plugging in a different variable, right? So we would have like 3a squared minus 4a minus 5. And that's even easier because there's not really any kind of simplification that we needed to do after that. I could also plug in a more complicated expression into that. Instead of just plugging in a, what if I wanted to find the value of the function for 2a minus 3? So that means everywhere in my original function, everywhere I see this x, I'm going to replace it with this, right? Just like I replaced it with a 4, I replaced it with an a. Now I'm going to replace it with an entire expression, okay? So that gets a little bit more complicated, but this is going to tie into this difference quotient that we're going to do in a few minutes, okay? So this is exactly the same thing. You just have to be a little extra careful when you're evaluating it. So in my original function, I had 3x squared. So now I'm going to replace that x, 2a minus 3, square that. So this is my 3x squared minus 4, and then I have another x, but I'm going to replace it with our expression, and then our minus 5. Okay, and then we have to evaluate that. And again, be super duper careful with your algebra. Because if you make some algebra mistakes, it's gonna sort of mess up your whole thing. So like for here, 2a minus 3, this whole quantity squared, we're not killing puppies, right? So we're not gonna say 4a squared minus 9. That's not what's happening here, right? We have to multiply out. This is a binomial being squared. So this is 4a squared minus 12a plus 9. And then I can bring the rest of this stuff down, or you can go ahead and distribute the 4 if you want. But I'm going to have to distribute my 3 through all of this stuff. I'm going to have to distribute this negative 4 through all of this stuff. I've still got my minus 5 on the end. Excuse me. If I do that, get all my like terms together, do all my simplifying, I believe it comes down to 12a squared minus 44a plus 34. Double check that. Is that what I wrote? I think that's right. But you got to be super careful, right? Like, I think, you could probably agree that the most common mistake is going to be right here, that people are just not going to square that correctly. They're not going to do it so that it ends up being a trinomial. So just be super careful, okay? You can do the same thing if I wanted to do like f of x plus h. You're going to see this specific expression again in just a minute in our difference quotient, right? But it's not really any different than saying 2a minus 3. Okay, it's just an expression, but it's going to have a little bit more meaning to us in a few minutes. But same kind of thing. I would just do x plus h squared minus 4, x plus h minus 5. And then again, I'd have to go back through. We'd have to like FOIL this out, or whatever method you like to do when you multiply your binomials. We have to distribute our 3, distribute our 4, all that stuff, like terms together. So it would be very similar to this one up here, okay? So let's go back up for just a second to this first one. Okay, so back up to this first one, we had our function and we were evaluating this function at a particular value of x, right? And we said, okay, we worked this out and we got 27. So we said we could write that as a point 427. Our x value was 4, our y value is 27. We could also say, and this is a little bit of a different notation that you probably haven't really seen because we don't really use it that much. But I could also say that my x value is 4, and then my y value is f of 4, right? Because this is, my x value is 4, and then this means, well, what's the value of the function when x equals 4? That's what we set up here, right? What is the value of this function when x equals 4? Well, that's another way of saying what's the y value, right? So these two, these are basically the same thing. I'm just interchanging the 27 with the f of 4, which we did up here, right? All of this stuff is equal all the way across. So f of 4, in this particular case, is equal to 27. So I could write the point this way, or I could just switch this out and write it this way, okay? Okay, so we know how to evaluate, I can speak. We know how to evaluate functions. And we can, you know, we can get a little bit more complicated with our evaluations. We just have to be very close and pay attention to our algebra, make sure we're not making silly algebra mistakes. The other thing that I wanted to talk about really quickly is, let me think, do I want to talk about this? Well, so yeah, I guess I'll kind of show you this briefly. Okay, so I have here a parabola, and I have labeled some points on this parabola. Let me slide this down a little bit so you can see that top point. So this is similar to what I was just talking about with like labeling points. So here, I've marked off some points here. We have f of 0 is 0. So again, if we're thinking about writing these as points, that means we have the point 0, 0. If I plug in 1, so my function is x squared up here. Sorry, can't see that. Up here in the top corner. Our function is just a, you know, parent function of a parabola, x squared. Let me write that over here where you can see it. Let's put it down here. F of x equals x squared. There we go. Okay, so if I plug 1 into the function, what is the value of the function when x equals 1? The value of the function is 1. So we'd have the point 1, 1. What is the value of the function when x equals 2? Value of the function when x equals 2 is 4. So we have the point 2, 4. And then what is the value of the function when x equals 3? That's 9. So we'd have the point 3, 9. But again, I could also write these as 0. My x value is 0. My y value is f of 0. My x value is 1. My y value is f of 1. My x value is 2. My y value is f of 2. Slide this whole thing down. My x value is 3. My y value is f of 3. Okay. So I'm just kind of showing you that notation because of what we're going to do with the difference quotient in just a second. And I didn't want anybody to get confused if they saw this kind of something that looked like this in the y spot. I didn't want anybody to get confused because those are interchangeable, right? F of whatever, f of x, f of 3, f of 2, f of 1, f of 0. Okay, the thing that you have to sort of just keep in mind is that a long time ago, when you first started to do functions, you just said like y equals something. But then, like I said, you got a little fancier and you started using f of x. But those are interchangeable, right? So hopefully, as we go through this, some of the notation that you'll see, hopefully that won't be confusing for you guys. I hope I can make it not be confusing for you guys. Okay, So let me get a new page here. And let's see, we're done with that one. Okay. All right, so difference quotient. All right, so this is probably like the first thing that you will start to talk about or look at in calculus next year. Both the AB class and the BC class and even the on-level class. I mean, this is across the board. Just one of the first things that you, maybe the first thing that you talk about in calc classes. So the thing, sort of one of the basic ideas that takes up a lot of time in calculus is thinking about how a function is changing as the x values change. So this is, again, not a new concept to you, as you will see as I go through this in just a minute. This is not a totally new concept to you, but you're just building on the part that you are familiar with, okay? So for calculus, one of the main things, and you'll see this, I'm just going to jot down some notes, but then I'm going to show you a site in just a second that's going to say a lot of this on it as well. But I wanted to kind of write it down as we go instead of me just reading to you off of a website. So one of the big ideas that people who study calculus are concerned with is how fast a function's value is changing as x changes. So you guys are familiar with this concept. This is just rate of change. And you guys have done rate of change in a few different ways. So the earliest thing that you did with rate of change is with linear functions. So for linear functions, when you talk about rate of change, that's just another way of saying that we're talking about the slope of the line. So you learned slope, and you learn the slope formula, y2 minus y1 over x2 minus x1. And if your teacher was feeling fancy that day, they might have even put this delta y over delta x, which means the change in y over the change in x. This is a Greek letter. It's not just a triangle because it's math. It's actually a Greek letter, delta. Delta, this Greek letter is one of those that always kind of means the same thing. Like sigma, like the big capital sigma that we saw with the sequences and series. Anytime you see that big capital sigma, it means you're going to be adding stuff up. That's the case in math. You might see it in your science class, like in bio or something, or even, I don't know, maybe in chemistry or physics. You see that sigma, it means you're adding stuff up. Delta is the same way, this little triangle. If you see that, it means something is changing. You could see that in all of those science classes as well. Physics, bio, chemistry, probably. So some of you may have already seen that symbol. If you haven't seen that symbol, that's what that means. It just means something's changing. So change in y over change in x. So that's kind of your first experience with rate of change, is just finding the slope of a line, right? Way back at the beginning of algebra. And then you got a little fancier and you started to look at functions that were not linear. You expanded out your knowledge of functions. You learned about quadratic functions. You learned about exponential functions. Maybe you learned about polynomial functions. That's what I'm going to use for this next bit. So for polynomial functions, they're really curvy a lot of times. So you could have some crazy polynomial function. Looks like that has a lot of twists and turns in it. And we want to know, perhaps, from this point to this point, say, what is the rate of change between those 2 points? So, well, there's a lot of stuff going on, right? Like there's a lot of wiggles and stuff happening between these 2 points. So what sort of ends up happening is we're still doing rate of change, but now because there's a lot of like other changes in the middle, when you get to stuff like this, when you get to graphs like this, it's not really called average rate of change. They put, or not rate of change, they'll put average in front of it. So average rate of change. But you're still kind of doing the same calculation, right? You're taking these 2 points. Maybe this is x1, y1, this is x2, y2, and we're still doing the same thing. We're doing y2 minus y1 over x2 minus x1, change in y over change in x. We're still kind of doing the same thing. We're calling it average rate of change to sort of account for the fact that there's other ups and downs in between, but overall, so you can sort of think about like a line going through those 2 points. And what we're really calculating when we do average rate of change is we're calculating the slope of this line between those 2 points, just like we would up here for linear functions. I mean, that's what this is, right? This is a linear function. But we just have to keep in mind that, you know, over this time period, this is the change, but there are other like minor changes happening in between. So what we use for this, because this is going through 2 points, we're using a secant line. That's the thing that hopefully you remember from geometry. We talk about secant lines and tangent lines. So a secant line cuts through 2 points, and a tangent line just touches at a single point and just kind of barely like brushes. Usually we do secants and tangents when we talk about circles. So you say, oh, the secant line cuts through the circle at 2 points, but you can also have it cutting through other things like a function. And then a tangent line just barely touches at a single point, kind of brushes the outside edge of that circle. All right, so we have our basic slope, linear functions. You get a little fancier, sort of call it average rate of change. It's not really slope, but it kind of is, because you're sort of calculating the slope of that imaginary secant line. All right, so when you get to calculus then, you get even fancier, and you start talking about instantaneous rate of change. Instantaneous rate of change. An instantaneous rate of change, and I promise I'm getting to the difference quotient, but I got to kind of walk you through all this stuff first. So to make that make sense. So the instantaneous rate of change is the slope of the line tangent to a function at a single point. The slope of the line tangent to a function at a single point. So all this stuff that you've done up to now, when you've talked about slope or rate of change or average rate of change, you've needed 2 points to be able to calculate that. But when you get to calculus, you don't need 2 points anymore. We're talking about instantaneous rate of change, the slope at a single point on the graph. Just one single point. All right, so this is where the difference quotient comes in, okay? So, I'm gonna get a new piece of paper. All right, so here's where the difference quotient comes in. So I'm gonna sort of give you the formula or the calculation that we use to find the difference quotient, and then I'm gonna sort of explain where it comes from and what you're actually doing when you're using this calculation, okay? It's always crooked. All right, so our difference quotient. All right, so just from the title, you can probably predict what two things you might see in this calculation. So difference quotient has a difference, has some subtraction, and it has a quotient. It has some division. All right, so here's our calculation. And I'm going to show you where all this comes from and what all this is. So on the top, we have f of x plus h. See, I told you you're going to see that again in just a second. F of x plus h minus f of x divided by h. Okay? Okay. So here's what's happening. We have, and I'm going to sketch a little bit of this first, and then I'm going to switch over to a really nice website I found that has a little demonstration that I can show you of this. But I'm going to sort of sketch some of this on paper first, so you can kind of do this with me if you want. All right. I feel like I should probably try to do some of this in pencil. Okay, so I'm just gonna make what could be perhaps like a part of a parabola or something. It doesn't really even matter what the function looks like that you use. But let's say we have something that looks like this. Okay, and we have, let's say this point that I'm gonna call, I'm gonna do this in red. Can't really see that red. And I'm gonna call this point P. And I wanna label the coordinates for point P, okay? So let's X coordinate. And then I'm going to do the same thing for Y, except I'm not going to call it Y. I'm going to use our fancy notation for Y. I'm going to call it f of x. Okay, so my coordinates for this point P, I have x and f of x. And notice back up here in this formula, I have an f of x value. Okay, so we're going to use this up here. Okay, so I have this point P, and I'm going to label another point a little farther up. We'll put this guy maybe like up here somewhere. Do him in green. And we're going to call that point Q. And I'm going to kind of mark off, I'm going to put in dotted lines. I'm not going to label anything yet, but I am going to put in the dotted lines. Okay, so, you know, we could give some labels to these, which we are going to do in just a second. But we're going to base these labels off of these guys over here. Okay, and what I mean by that is if I wanted to know the x coordinate of this point Q, I could say, okay, well, I'd say, oh, it's like that far. right? Like I go from the origin over and I say, well, the x coordinate is that much, whatever that might be. But instead of doing that, I want to think about it as being this distance that I moved over for my point P plus a little bit more. Okay, so I'm going to call this little bit more distance, that little distance in there, that's H. So notice again up here in this formula, we have some H's that we see in there. H is this extra little distance between these two x coordinates. Okay, it's this extra little bit right here. So when I get ready to label this x coordinate for my point Q, I can say, well, it's x plus h. So I'm going to call this distance x plus h. And I know that's kind of hard to see. All right, let's see if I can get in a little closer on that. X plus h. And then just like I did with my point P, I had the x coordinate and I had the y coordinate. So I had x and f of x. I can do the same thing here. This is my x coordinate. This expression is my x coordinate, and then my y coordinate would be f of that expression, f of x plus h. F of x plus h. Okay, so hopefully you're still with me. I didn't lose anybody. I'm going to kind of go through it again. So I've got my 2 points, P and Q. I've labeled my point P. This is the x coordinate. I went over a certain distance x. And then the y coordinate is f of x. It's the value of the function for this value of x from over here, right? Just like we were kind of doing at the beginning. That's why I wanted to go over that stuff. And then for point Q, I went to get to this x coordinate, I went over this amount plus an extra amount. So my expression for this whole distance is this x plus this little extra bit, x plus h. And then the y coordinate that corresponds to that is the value of the function, or the value that I get when I plug this into the function. Okay, doesn't matter that we don't really know what this function is, right? It's going to be the same no matter what function you're using. Okay, so I have my coordinates for point P in red, and I have my coordinates for point Q in green. Okay, so let's say that I wanted to find the average rate of change between these 2 points. The average rate of change between these 2 points. So we just said a second ago on a previous page that the average rate of change that was y2 minus y1 over x2 minus x1. So if we just sort of think about point P as being my first point and point Q as being my second point, I can take all of this notation and just plug it into what we would normally use for slope or for average rate of change. Okay, so let's do that. So normally I would go y2 minus y1. Well, this is my y2 value. this is point number 2, so this is my y2 value, and this is my y1 value. So this is f of x plus h minus f of x, that's just y2 minus y1. And then on the bottom, I got to do x2 minus x1. Well, that's just this guy, this expression, minus this one. On the bottom, I'm going to have x plus h minus x. Move that down a little bit so you can see. Okay, so all I've done is I've basically just done the slope formula or the average rate of change formula from point P to point Q. We did y2 minus y1, we did x2 minus x1, and look what's going to happen on the bottom. I'm going to have x minus x, so they're going to subtract out. The top is going to stay the same. And what I end up with is this difference quotient formula. Okay, so that's where this formula comes from. You're calculating the average rate of change between any 2 points on this curve. Okay, any 2 points on this curve. We have this first point that we're calling x and f of x, and then we move over a little bit. We add in this extra little distance that we called h. So now this one has coordinates x plus h, and then f of x plus h. And we're just doing the slope formula with this, okay? But again, what's really happening here, if we're finding the average rate of change between these 2 points, what's really happening here is we're sort of imagining that we have this secant line again, right? And we're really just calculating the slope of this sort of imaginary secant line that's going in between from point P to point Q. So how does this relate to what I just said about instantaneous rate of change? Where the heck does that come in, right? So I'm going to switch over. Ugh, got to reposition. I'm sitting on the floor here. This is not the most comfortable thing. Okay, so I'm going to stop that camera. And I'm gonna, let's see, how do I want to do this? I want to get rid of that. And I'm trying to think, where do I want to go? Actually, maybe I do want to go back here. And no, that's not what I want to do. Sorry, guys. Bear with me. How do I do this? Can I do this? Okay, this is what I want to show you. All right, so here is essentially the same picture that I drew. And I can put in point P, and I can put in point Q. Now, the downside to this little website that I don't love is that it uses some different notation, and I'm not really sure why. But you'll notice, like right here, instead of X, it's using C. So it's saying, okay, this is point P, and it's got the X and Y coordinates here. So instead of X and F of X, we've got C and then F of C. So hopefully that is not too confusing to people, but I wish they would use X and F of X. But anyway, so here's our point P. We've got our coordinates C and F of C, and then we have our point Q. And notice the X coordinate, we're doing this distance C plus a little bit more, right? This is our extra. This is what we called H. This distance in here is what we called H. They're calling it delta X. They're calling it the change in X. So this is the extra little bit that got added to our original X coordinate that got us to here. So this whole distance from the origin all the way out to here is c plus a little bit more, okay? So that's the x coordinate of that point right there. This is where it starts to look a little bit more complicated. This is just the x coordinate. And then the y coordinate is f of all of that stuff, okay? So we had x plus h, and then we had f of x plus h, okay? So they're using some slightly different notation, but it's the same idea, okay? So if you go back up here, and I think I'm actually gonna send you guys the link to this site. This is actually just something that somebody made in GeoGebra. I mean, you could look up here, I suppose, and just make note of what that is, but I'll send out the link in case anybody wants to actually like go in here and play around with this. So this is kind of the stuff that I was going over at the beginning. It talks about, it says differential calculus is concerned with finding out how fast a function's value is changing as x changes. We call this the rate of change for the function. So it talks about average rate of change, and then down here at the end it says we can also find the slope of the line tangent to the function at a single point, which turns out to be equal to the function's instantaneous rate of change. Oh, excuse me, I had to get a drink. Okay, so if we go back to this picture, so let's suppose there's one thing that I'm going to put on this picture that I did not put on our drawing because I thought it would be, it would get a little too messy. But the thing I didn't put was the tangent line. So I'm going to take off this point Q for just a second. So let's say we have this one single point on this function, point P, and I can put in a tangent line to point P. And so the idea that it's talking about up here, it says with instantaneous rate of change, we can find the slope of the line tangent to the function at a single point. So we want to find the slope of this line. And that's a function's instantaneous rate of change. So it's essentially like finding the slope of this blue function. What's the slope at just this single point right here? It's like instantaneous slope. Okay, so I'm going to leave that on there, and I'm going to put my Q in there. And then I'm also going to put on the secant line. So that was the last thing that I drew on my picture. I put in that secant line, okay? And the cool thing about this site, and the reason why I wanted to show this to you, is because here's where all of this kind of relates to instantaneous rate of change. So if you think about that difference quotient formula, which again was just essentially like the slope formula, right? We did the change in y, the change in the two y coordinates, and then we did the change in the two x coordinates. So what happens and what you're going to talk about next year when you talk about this in calculus, and you may even see something similar to this, kind of a demonstration similar to this, is what happens is we want to take this distance and we want to close it in. We want to bring these points closer and closer and closer and closer and closer in together. And when we do that, if you watch this green secant line, if I start bringing this point closer in, notice that my secant line is changing, right? The slope of that secant line is changing. And as I'm coming in, this distance here is getting smaller. It's getting smaller, and it's getting smaller, and it's getting smaller. So again, there's my H distance. It's even smaller. Bring it in a little bit more. My H distance is getting even smaller. And notice what's starting to happen. This secant line is starting to get closer to this tangent line. And if you keep bringing them in and keep bringing them in and keep bringing them in and keep bringing them in. Eventually, it's the same thing, right? Our secant line lines up with our tangent line. And what we've done down here is we've taken that extra little stuff that we were adding, that H distance that we put on our picture. We've made that H distance 0. Okay, we've essentially made that H distance 0. We've moved these points closer and closer and closer and closer and closer together. And we've made that distance basically go to 0. So what you're going to see, I'm going to show you a different type of, hello, me again, a different type of notation. Make this bigger. Okay, so we're back to our picture. Okay, so we're bringing this point down closer and closer and closer and closer. We're closing up this gap. Every time I move this point down, this gap closes. So we're closing up that gap, which means we're essentially making our H value go to 0. So if you calculate just this by itself, you're calculating the slope of this secant line, okay? But if you put some extra little notation at the beginning, that looks like this. If you add this in the front of it, that means that you are essentially closing up this gap right here. You're sliding this point down and you're closing up that gap, and your secant line is turning into your tangent line like we saw on that picture. This part right here, this is a limit. You talk a lot about limits in calculus. Just too much for me to get into right now, but that's what this means. This is the limit of this calculation, the limit as H goes to 0. So as we move this point down and we close up this gap, as H goes to 0, what are we getting when we do this calculation? Okay, that's the difference quotient. So there's a lot of explanation. I'm going to show you some example problems. Like, you're probably sitting there thinking, okay, but what am I going to have to do, right? Like, how does this translate to like a homework problem? All right, so that's what we're getting to. So let me, how do I want to do this? Let me switch over again, and let me see if I can find the page I was looking for. Let's go back to our picture for a second. And there's more stuff down here at the bottom. I'm not going to read through all of that. It's basically what I was explaining in the picture. But you'll see this down here, this limit, and this is another way of writing another notation that you'll see. And you see the word derivative up here. Basically, when you do this calculation, you're finding the function's derivative, which is another way of saying instantaneous rate of change, okay? So you're pretty much like half of your year of calculus is going to be devoted to finding derivatives of different functions and learning different rules about derivatives and all that. So you'll learn everything you ever wanted to know about derivatives next year. Okay, so let me go back to, I'm going to get rid of this. I want to go back, and so I'm going to do a few of these with you as practice, okay? So I'm going to jot some of these down so I don't have to keep coming back to this. So we're going to do some linear stuff, and we're going to do some quadratic. And then you guys will also have, I think, the last two problems on your homework sheet are going to be radical functions. So I'm going to leave those to you to do on your own. There's going to be an answer key in there. So let's do part D. Let's see, 2x squared minus x. And then we'll do the one from the beginning that I gave you, that quadratic function, 3x squared minus 4x minus 5. Okay, so you're going to use the difference quotient on each of these functions, and this is exactly what you're going to have to do on your homework. Okay, so I'm going to show you how this is going to work. Okay, so let's put our difference quotient up here again so we remember what that is. F of x plus h minus f of x over h. Okay, so let's say for the first one, we're given a function, and that function was 2x plus 5. So if we want to do this calculation with this function, it's that this is just like what we talked about at the beginning of the video, function notation. So like, you know, we did f of 4, which meant we had to plug 4 into the function. Well, this first part of this calculation says we want to do f of x plus h. So if I want to do the difference quotient, I'm going to do f of x plus h. Sorry, I don't know why I'm writing that down. So f of x plus h is just going to be the function, this function, with x plus h plugged in here. Does that make sense? So if this were f of 4, we would, or if this were f of 4, sorry, we'd plug in a 4. But it's f of x plus h. So we're going to plug this into here. So I'm going to have 2x plus h plus 5. Okay, that's the first bit of my calculation. That's just this bit right here. If it's helpful to you, you can put that in brackets and then do your minus sign. This part is just the function itself, right? F of x. That's just 2x plus 5. Okay. So this is f of x plus h. We've just plugged x plus h into our function minus the original function. And then this is all over h. Okay. And now we have to go back and evaluate and simplify if we can. So on the top, if I distribute this 2 through, this is going to be 2x plus 2h plus 5. And then probably it would be a good idea to put this stuff in brackets too, so that when I do my subtraction, I remember that this minus sign is going to go to both of these. So this is going to be minus 2x minus 5 over h. Then we go through and we simplify, and I say, okay, well, 2x minus 2x, those are going to cancel out. 5 minus 5, those are going to cancel out. And then we've got 2h over h. Those are going to cancel out. And then I simplify to a 2. Okay. So I did the difference quotient for this particular function, and it simplified down all the way to a 2. So this original function was a linear function. So when we do this, we're thinking about this as sort of an instantaneous slope. We're finding an instantaneous slope. So it should make sense to you, sort of. I know it's still kind of a new concept, but it's kind of interesting that this came out to be a 2, because that's the slope of our line up here. And since this is a linear function, the slope is the same the whole time, right? So the slope is always going to be the B2, the instantaneous slope, no matter where we're looking on this function, the slope is going to be 2. Okay? Let's do another linear one. So let's say I have a function 3 minus x. 3 minus x. All right, so I'm going to do the same calculation. F of x plus h, so that means that I'm going to take x plus h and plug it into my function. So I'm going to have 3 minus x plus h. That's the first part of my numerator, minus just the function itself, f of x. 3 minus x. So this is f of x plus h minus f of x over h. All right, so I'm going to go through, I'm going to deal with all my negatives and stuff. So this is going to be 3 minus x minus h minus 3 plus x over h. Oh, so something similar happens. 3 minus 3, those are gone. Negative x plus x, those are gone. I've got negative h over h, so that's going to make a negative 1. Again, that's kind of interesting because this was a linear function that has a slope of negative 1. And again, it's a linear function, so the slope is the same, like everywhere, right? We don't have any pieces of the function that are going to have a different slope. It's just always negative 1. And so this is telling me that my instantaneous rate of change is also negative 1, no matter which part of the function I'm looking at. That's what I'm getting as my slope. Makes sense. Makes sense to me because this is a linear function. My slope's the same no matter where I'm looking. But let's say we don't have a linear function. Let's do like a quadratic. Okay. So I'm going to put my thing back up here. Okay, so what is this, C, I think? So let's say we have a quadratic function, 2x squared minus x. All right, same thing. I'm going to do f of x plus h. So I'm going to take this x plus h and put it into my function. So this one's going to be a little bit more complicated. So I've got my 2x plus h squared minus x plus h. So this part, this is me just plugging in x plus h into my function, right? I'm evaluating at x plus h. So this is, all of this in brackets is just this first bit right here. Minus f of x. So f of x is just the original function. 2x squared minus x. And then this is all over h. Okay, so now I got to go back through and I got to work this out. Be careful here. Remember, this is, you got to multiply that out. So that's like, we kind of come over here. This is x plus h and another x plus h. Okay, so we're going to have a 2. If I multiply all this out, that's going to be x squared. That's going to be plus 2hx plus h squared. Let's see, I'm going to go ahead and do my negative through this. So that's going to be minus x minus h. I do that. And then I'm going to go ahead and do my negative here. So that's going to be minus 2x squared plus x over h. I got to do my 2 through all of this. So that's going to be 2x squared. That's going to be 4hx. That's going to be 2h squared. Let's see, minus x minus h minus 2x squared plus x over h. All right, so let's see what cancels out here. 2x squared minus 2x squared. Got a minus x, I got a plus x. So let's see. I've got 2h squared plus 4hx minus h over h. I don't really know why I just switched those around. It doesn't really matter. But what I would like to do is to be able to cancel out some of these h's. And I can do that if I break this into 3 separate pieces. So I got 2h squared over h. I've got 4hx over h. And I've got minus h over h. So let's see. This cancels with one of these. Those are going to cancel. This cancels with that one. So I've got 2h plus 4x minus 1. All right, so this one is interesting because it didn't just simplify to a single number. We sort of have a thing that looks like a function, but it also still has an h left in it. But remember what we said when we, in that illustration I showed you and in that picture we drew, we said that when you're talking about instantaneous rate of change, you're essentially, the concept is that you are making that h go to 0. H was that extra little distance. If you need to look back at your picture, that was that extra little distance that we had because we had distance between point P and point Q. But when we moved those points closer together and we got that secant line to overlap with that tangent line, they became the same thing. The h value closed up, right? It went to 0. So what's going to happen is you're going to do some of these and you're going to get down to the end and you're going to have some with h's in there. But then we can say, oh, well, we made our h value just go to 0. So any of those are going to become 0, which is going to wipe out that term. So really what we have, a 4x minus 1. So this is telling me, and this is, again, you know, don't worry if you don't completely understand this whole derivative tangent line concept, because like I said, you're going to spend tons of time talking about this next year. But the idea, just to sort of take away, is to kind of, number one, understand the algebra that's happening up here and how we're setting this up and how we're simplifying this. And then what this is telling us at the end is how to find the instantaneous rate of change. But it's not just a single number anymore, right? And again, maybe, hopefully that makes a little bit of sense to you, because what was this up here? This was a parabola, right? So depending on where you're looking on the parabola, you can have a different looking slope. Like one side of the parabola is a decreasing function. It's kind of going down. It's got a negative slope. The other side of the parabola is going to have a increasing positive sloping side, right? So for our instantaneous rate of change, it's not just a constant number anymore, because we don't have a constant function. We have a function where, depending on where we're looking, the slope could be changing. That instantaneous rate of change could be something different. So that's sort of what this is telling us. And you don't really need to necessarily do anything with this right now. You will eventually, you will in calculus. But for right now, we just want people to kind of understand what we're doing with this formula. We're setting this up. We're calculating this. We're kind of doing the algebra involved and simplifying this down as much as we can. Okay. All right, I'm going to do one more with you. This is also another quadratic. This is a little more complicated too. All right, so our function is, I think this is D maybe, 3x squared. This is what we started with at the beginning, minus 4x minus 5. Okay, so I'm going to do f of x plus h. That means that everywhere I see my variable, I'm going to replace it with x plus h. I'm going to have x plus h squared, x plus h. All right, all of that is my first bit. Okay, minus f of x. Well, f of x is just my original function. 3x squared minus 4x minus 5. All of that goes over h. Okay, so we're going to go back through, and I'm going to try to multiply some stuff out. We already know what this is. We said a second ago, we did x plus h times x plus h. Okay, so I'm going to have my 3. This is going to be x squared. This is going to be 2hx. This is going to be h squared. I'm going to go ahead and do my negatives as I go through. So this is going to be minus 4x minus 4h minus 5 minus 3x squared plus 4x plus 5. Whew. So you can see how complicated these can be in terms of, well, I don't want to say complicated, just more tedious. Imagine if you won't have any of these on your homework for tonight, but imagine if you had like a cubic formula, so that this was x plus h cubed. So you had to like do another one on here. So you can see that they get, you know, pretty lengthy and pretty tedious real quick. All right, there's my h on the bottom. All right, so then I got to do my 3 through all this, and then we can start to simplify. All right, 3x squared. This is going to be 6hx. This is going to be 3h squared. Gotta bring all this down. Minus 4h minus 5 minus 3x squared plus 4x plus 5 all the way over h. Okay. Oh, let's see what cancels out. Oh, 3x squared minus 3x squared. I see a minus 5 plus 5. I see a minus 4x and a plus 4x. All right, so I've got these 3 things that all have h's in them. So I'm gonna skip a step from last time. I'm just gonna go ahead and break these into 3 pieces with this denominator under each one. That'll save me a step. So I'm gonna have 6hx over h. I'm gonna have 3h squared over h, and I'm gonna have minus 4h over h. Okay, so these h's cancel. This one cancels with one of those, and these cancel. So we have 6x, we have 3h, and we have a minus 4. And again, remember that in our calculation, we're assuming that our h distance is going to go to 0. So that's going to eliminate this term that's got the h in it. So we end up with 6x minus 4. 6x minus 4. So this is telling me that this expression right here is in some way related to my instantaneous rate of change for this quadratic function that we started with. Okay. So your job on your homework is to do this stuff, is to do this algebra. Okay. So a few of them are going to be linear, like the first two that we did. A few of them are going to be quadratic, like this. Takes a little bit longer because you got to like FOIL all this stuff out and that kind of thing. And then I think the last two, maybe three, have a radical in them. It's a radical function with a square root. And again, the answer key is going to be in there, so you can check your answers and see how you're doing. Okay. Let me come back to this. Ooh, that was kind of a marathon. Sorry about that. Hopefully you took some breaks in there, came back, got a snack, that kind of thing. So that's it, ladies and gentlemen, boys and girls. This is my last video. The homework, like I mentioned earlier, is going to be in teams this time. It's not an Alex thing. It's going to be in teams. But that's it. I'm a little sad. I got to be honest. I have to say goodbye on a video. I don't like that. I'm a hugger. I like to hug people on the last day. I don't like to say goodbye on a video, but this is where we are, so that's what I have to do. But I hope you guys were awesome this year, and I promise I'm not just saying that. You really were. I am lucky in the classes I teach because I get the cream of the crop. I get you guys, and I don't like to hand you off, but I have to. But it was good. I enjoyed each and every one of you in class this year. And let me know, even though we don't have, new stuff later on, if you need me, I'm here. I'm always here for questions. You guys have to come back and visit me next year. Pop in and say hi on your way to calculus, or wave at me down the hall as you go into calculus. But yeah, you guys can always come see me. I know probably every teacher that I know, and at least the ones at Alpharetta, the majority, the good ones, we'll just leave it at that, the good ones, would always say the same thing, which is that once you are in my class, once you're one of my kids, you're always one of my kids. So that never changes. So yeah, I hope you guys have a good summer. Those of you that have AP exams coming up, good luck. I'll be honest, I'm real glad I wasn't teaching AP stats this year. I dodged a bullet on that one. But you guys will do fine, and good luck, and have a good summer, and that's it. Bye guys. I will see you again. I promise. We'll see each other. It'll happen.